solving radical equations. We're just going to jump right into working through some examples, and then we'll summarize the procedure. And then at the conclusion of the video, we'll do some more challenging examples. So in solving an equation, we're trying to find values of x that make this equation true. And to do that, we're trying to isolate that variable with the utilization of inverse operations. Now, with radical equations, one of our primary objectives is to get rid of the radical. We want to remove it from the equation. And to do that, when I'm working with a square root, we are aware that we would square or raise that side to the power of 2. Now, if I were to do that at this point, to try to remove that radical, that's going to create a lot of work, because raising this whole side to the power of 2 is going to require me to multiply this entire expression by itself, and that it's going to be a lot of distribution, a lot of multiplication. And we can avoid that if we isolate this radical first. So usually your first move in these radical equations, try to get the radicals isolated. That way, when you go to remove the radical, there's not additional algebra that's unnecessary. So I'm going to move that 7 to the other side of the equation through addition, and we're at this point. I have a 2 coefficient in front of this square root that I could move to the other side through division and get to here. Now this radical is completely isolated, and this would be a good opportunity to remove that radical by squaring both sides. So a square root requires an exponent of 2 to cancel out. So we have 4 equals x minus 7, and now all I'm left with is a simple polynomial, in fact linear equation, that is very easy to solve. I just have to move that 7 to the other side, and we get x equals 11. So after removing the radicals in the equation, we should just have a polynomial equation to solve. Now, backing up a few steps before we move on to the next example, let's go back to this second line. And let's say that after moving that 7 to the other side, let's say that this was a 2. Negative 2, and then as a result, we get 5 over here. In this case, it wouldn't be really the best idea to divide both sides by 2 if you're not comfortable working with fractions. So I could isolate the radical there, but then I'm going to have to square a fraction and work off of that, which isn't the end of the world in this example. But as things get a little more complicated, it's not really that big of a deal to leave that 2 in front, because squaring both sides at this point, all I have to realize is that I have to square that 2, because I have 2 terms in this parenthesis that are being squared. The 2 gets squared to 4. The square root of x minus 7 gets squared, and that cancels, and I get this. And I can work off of that. I can distribute that 4 and work around dealing with that 5/2. So something to think about when going through these examples: is it worth your time to move that coefficient in front of the radicals to the other side? Think about, do I want to work with fractions right off the bat? Yes or no? It's really a preference thing. So, second example. We know we want to remove the radicals. We're dealing with 2 square roots here. And to remove the radical, I would want them to be as isolated as possible to avoid any unnecessary algebra if I can. At this point, on the left, we have a 5 coefficient in front of that square root. If I move it to the other side through division or through multiplication by its reciprocal, then the other side now has a coefficient. So really moving that 5 to the other side, yes, it will isolate the radical on the left, but then it doesn't isolate the radical on the right, which is isolated to begin with. So this is really as isolated as we can get this equation. So at this point, we know we want to remove the radicals, so we're going to square both sides, and as stated in the previous example, we have 2 terms being squared here. The 25 as a result of squaring the 5, and then square root of x minus 1 becomes just x minus 1 and x plus 1 there. Now, could I divide both sides by 25? Yes, but I'm going to be working with fractions, so it would be better to distribute this 25 to avoid the fractions for now, if there are going to be any. We have a linear equation here to solve, so I'm going to get my x variables on the same side. I'm going to subtract x. I'm going to move that negative 25 to the other side. And we're going to get 24x equals 26. So x equals 26 over 24, which reduces to 13 over 12. Here, we want to remove the radical, so get it isolated. Again, I could square both sides at this point, but squaring this side is going to require that thing times itself, and that requires a double distribution. Again, algebra that we want to avoid if we can. So all I have to do is move that 3 to the other side and get the following. Now at this point, when I square both sides on the left, I don't have to worry about distributions with radicals. So squaring this left side, it'll cancel out. Now squaring the right side, 2x minus 3 squared, is 2x minus 3 times 2x minus 3. So in the end, I do have to do this double distribution, but would you rather do it with expressions that don't have radicals or with expressions that do have radicals? So by moving the 3 to the other side, we can do the distribution without the involvement of the square root, as would be the case if I squared both sides right from the get-go. We're going to get 4x squared minus 12x plus 9. Okay. At this point, we have a quadratic. So when we have a quadratic to solve, if a linear term is present, we must set the equation equal to 0. So I'm going to move the terms on the left to the right, and we're going to get minus 15x, and it looks like minus 4. We're going to factor this quadratic. There's no GCF to remove, but if I do a times c, I'm going to get negative 16. I'm asking myself, so we have to use split the middle because we have an a value greater than 1. So a times the c value from that standard form, ax squared plus bx plus c, gets me negative 16. What multiplies to negative 16 adds to negative 15, negative 16 and positive 1. So we're going to split the middle term with coefficients of negative 16x and positive 1. Now we have a grouping problem. Take a GCF out of this first group here. Take a 4x out. We're left with x minus 4. For grouping to work, we need what's left over after removing a common factor from the second grouping to match what's left over in the first group. So all I have to do is pull out a positive 1. And we see that the factorization is 4x plus 1, x minus 4. And therefore, my solutions are negative 1/4 and 4. Now, with quadratics, multiple solutions in radical equations, we must check our work for potential extraneous solutions, meaning we might have answers that are valid as a result of the algebra, but when we go to plug them back in to see if they satisfy the equation, they may not, in fact, be true. And that can happen often because of the restricted domain nature of a radical function, especially the even index radicals. So if we plug in both of these, you will see that one works and one doesn't. So if I plug in 4, we're going to get the square root of 25 plus 3 equals 2 times 4. So we're looking for the left side to match the right side. So if you simplify the left side all the way down, does it match the simplification of the right side all the way down? So we have 5 plus 3 equals 8. 8 equals 8. So check. So 4 is a valid solution. Now, as for negative 1/4, if I were to plug in negative 1/4, I'm going to get a positive value here, and then plus 3 equals 2 times negative 1/4. So I can already see a positive plus a positive is going to result in a positive number. Could that equal a negative number? No. So negative 1/4 is not a valid solution to the original radical equation, even though it was a correct solution to the quadratic that we found as a result of clearing out that radical. So what we would say for our final answer is that 4 is the solution, but negative 1/4 is extraneous. So it's going to be important that you check your solutions when solving radical equations, especially the even index radicals, the ones that you are required to raise a side to an even power for a cancellation. So far all we've seen are square roots, but we could have other types of radicals involved in the equation. Now, there's no radical explicitly drawn here, but we know fraction exponents or rational exponents indicate a radical is present. And the denominator of your exponent tells you what type of radical you're working with. So because the denominator of the rational exponent is a 4, this is the same equation as the fourth root of 5x plus 1 raised to the power of 1. So the numerator tells you the exponent of that expression that the power is associated with, or the rational exponent is associated with. So these are equivalent, and sometimes rewriting them in radical form is helpful for some people, but you don't necessarily have to do that. Now, this radical is completely isolated already, and we know the objective in solving radical equations is to remove the radical from the equation and ultimately solve the polynomial that is a result after the removal. So far, all the equations being square roots, we were raising both sides to the power of 2. But in this case, to get rid of a fourth root, we must raise both sides to the power of 4. 4 times 4 is 16, times 4 is 64, times 4 is 256. And then if we subtract 1, we're going to get 255. And then here, x should equal, it looks like 51. So we covered some basic radical equations. So let's just summarize the procedure. The first thing you want to do is we want to get the radicals as isolated as possible. In some cases that we'll see after this summarization, it's going to be difficult to isolate them, or you won't be able to isolate one versus the other. So we're just going to have to work through a longer procedure to solve. But if we can get the radicals isolated, then it's not difficult to remove the radical. All we have to do at this point is raise both sides to a power or an exponent value equal to the index of the radical in the equation, right? So that's important as well. So if we have square roots, we're going to want to square both sides. If we have cube roots, we're going to want to cube both sides. Fourth roots, raise both sides to the power of 4. So we want our exponent that we're using to remove the radical to match the index of the radical. And then once all the radicals have been cleared, we're going to solve the resulting polynomial. Once we have solved that, check your answers for extraneous solutions. So this first step, isolating as much as possible. We saw an example before, something like this. The one on the left, not completely isolated, but again, it's as isolated as much as possible, because if I move the 5 to the other side, now the one on the right isn't isolated. So we just try to do our best, and as we'll see in the examples that follow, sometimes we can't get them isolated at all, and we're just going to have to work through some messy algebra to get our answers. But this is a general approach. The primary goal that you want to keep in mind is you want to remove the radicals from the equation. Okay, so if you attempt to do something and it doesn't remove the radicals, see if you can manipulate further and still try something in addition to what you did to get rid of the radicals. You don't want them to be in the equation. We're trying to isolate that x variable, which is often inside of that radical, so it needs to be removed. So now we're going to look at some more complicated and more challenging examples. If you want to stop the video at this point, that's not a big deal. We've covered the more basic ones. But here, this is an example that I'm talking about where, yes, we have the radical isolated on the left, but the one on the right has this -2. And if I were to move that 2 to the other side, now the one on the left's not isolated. So how is this different than the one with the coefficient out in front? Well, when we go to square both sides to remove these radicals, the one on the right is going to require a double distribution. It's not just a matter of squaring the square root and then squaring that 2 and then calling it a day. So on the left, the radical cancels, but on the right, what we have is this, technically. Now, this isn't terrible, and we'll see why, because there's some nice things that result. When I make this first distribution, and then the second one, but the first distribution, square root of x plus 15 times the square root of x plus 15 is the same thing as the square root of x plus 15 squared, in which case the radicals disappear and I'm just left with x plus 15. Upon the second distribution, I can't distribute that 2 inside of the radical, so I can say it's -2 square root of x plus 15. Now, the second distribution, when I distribute the -2, that first distribution for the -2 into the second set of parentheses is the same thing as the last distribution when I distributed square root of x plus 15 to the -2. So I have -2 square root of x plus 15 again. And then -2 times -2 is +4. I can combine these two because the square root of x plus 15 and square root of x plus 15 match. So we're essentially asking ourselves, how many square root of x plus 15s do I have? Well, I had -2 for a total of -4 square root of x plus 15. And I'm going to combine that 4 with that 15 for like terms here to a 19. We have x equals x minus 3. So did we completely remove the radicals from the equation on that initial step of squaring both sides? The answer is no. We still have a radical present. But what we did was we went from 2 radicals in the equation down to 1. And from the examples that we started the video with, we are familiar with how to work with this. We're going to want to isolate that radical as much as possible. So still the primary goal is get rid of the radicals. So I'm going to move everything that's not involved with the radical to the other side if it's worth my time. Well, we're going to move this x over, and isn't that nice that these cancel out on both sides? And if I'm going to move this 19 over, by subtracting, I get -22 equals -4 square root of x plus 15. So this is what I was talking about before. Do I want to divide both sides by -4? Well, I'm going to have 22 over 4. So that's not a nice clean number. If that was a 24 on the other side, then it would divide evenly, and that would be worth my time. What I can do is we have negatives on both sides. So if I divide both sides by -1, we get positives. So I'm going to leave the 4 on the right, and I'm going to square both sides at this point. So I'll need a calculator for 22 squared. We're going to get 484 equals 16. So don't forget that 4 has got to get squared, and then that square root cancels, and we're left with this. I could divide both sides by 16. 484 is not divisible by 16, so I would get a decimal. It's not the end of the world, or a fraction. But let's distribute the 16. Subtract 240. And divide by 16, we're going to get 15 or 16 or x equals 15.25. There's my solution. Now we should check our solution. Now we're working with a decimal here, and if we use our calculator to check this, so if we did 15.25 minus 3, square root of that, and then we did square root of 15.25 plus 15 minus 2, you would see that the left side equals the right side after making those computations with the calculator. So yes, 15.25 is a valid solution. Next, pretty similar to the last one, but I just want to show you some algebra related to solving this one. So I could move that square root of x minus 3 to the other side, or I could move the square root of x minus 2 to the other side and create a scenario that's very similar to the last example. But I want to show you what it would look like if we have to do a double distribution where both terms are square roots. Okay, on the first distribution, square root of x minus 3 times the square root of x minus 3 is the square root of x minus 3 squared, so I just get x minus 3 left over. Now, the square root of x minus 3 times negative square root of x minus 2, I'm just going to write as the product of those two things. Now, I could combine them because they're both the same type of radical. They're both square roots, so I could write it like this after I make the distribution from the first term to the last term. So that's what just happened there. And I'm allowed to combine them underneath the same radical, again, because they're both square roots. And when I combine them, they're being multiplied together. Now, when I distribute this term into this set of parentheses, I'm going to get the same thing as when I got the product of that first term to the last term. So we're going to get this again. If you're wondering if the order of the x minus 2 and the x minus 3 inside the parenthesis matters, it doesn't. So with real numbers, which the x is going to be in that set, the order of multiplication doesn't matter, right? 2 times 3 is the same thing as 3 times 2. So these are technically the same terms, and I'm going to be able to combine them into one by saying how many square roots of x minus 2 times x minus 3 do I have? Minus 1 for a total of negative 2 of them. And then when we multiply the last two terms for the last distribution, negative times a negative makes a positive. Square root of x minus 2 times the square root of x minus 2 is the square root of x minus 2 squared. So I'm just going to get plus x minus 2 equals 1. So again, an example where I started with two radicals, I made a move or a decision to raise both sides to the power that's equivalent to the index in an attempt to remove the radicals from the equation. Upon doing that, I'm still left with a radical in the equation, but no big deal. But I went down from 2 radicals down to 1, and we know how to handle this. We're going to isolate the radical as much as possible, combining like terms and moving things over. So I'm going to leave this negative 2 for now. We'll see if it's worth our time to move it. Oh, this should be a 2. So x and x is 2x, so I'm going to have negative 2x on the other side. Negative 3 and negative 2 is negative 5, so I'm going to have a plus 6 over here. Now, it is worth my while to divide both sides by negative 2 because the terms on the right side are both even and evenly divisible. So I'm going to move that. So we get x minus 3. Now the radical is isolated, square both sides. It's going to cancel out on the left. Remember, when I square the right side, that's technically x minus 3 times x minus 3. And doing that double distribution is going to get us this. So what do I do at this point? I have a quadratic on the left side. I have a factored format on the left side. Now, I'm going to want to combine a bunch of like terms so I can see what the actual quadratic I need to solve is. So I'm actually going to distribute on the left to get this. And it turns out here that when I move things to the same side, or attempt to do that, the x squareds actually cancel. So I actually don't have a quadratic that I need to worry about here. And we have a linear. So if I move the 6x from the right to the left through addition, we're going to get x over there. If I move the 6 to the right through subtraction, we're going to get 3, x equals 3. So there's our solution. Now let's check to see if that does indeed work. So if I plug in 3, to the original equation, we're going to get square root of 3 minus 3 minus square root of 3 minus 2 equals 1. So is that true? So if I simplify the left side, does that simplify down to a positive 1? Well, square root of 3 minus 3 is 0, so we're going to have 0 minus the square root of 1 equals 1. So square root of 1 is positive 1, so minus 1. Does that equal 1? No, it doesn't. So these are not equal. Therefore, 3 is in fact not a legitimate solution and is extraneous. So the only solution we found as a result of solving this turned out to be extraneous, and therefore this radical equation has no solution. And last example, what if we have a bunch of radicals embedded within others? So a multi-layered radical equation. Well, as you may have guessed, we're just going to keep squaring both sides until we get rid of all of them. So if I square both sides once, I get rid of the first radical on both sides. I would do it again to get rid of the second layer. And I would have to do it one more time to get rid of this last one. But remember, we're squaring both sides, so I have to square this side when I remove that last one on the right. So we're going to get 9x squared plus 6x plus 1 equals 50x plus 6. So this is what the result is after removing all the radicals. We have a quadratic. Linear term is present. So we're going to set this thing equal to 0. And we're going to find out that this is factorable. No GCF to remove, so we're going to do a times c. We're going to get negative 45. What multiplies to negative 45 adds to negative 44. We're going to get negative 45 and positive 1. So we're going to split the middle with those coefficients. The order of the split doesn't matter, so I could have done the 1 first and the 45 second if I wanted to. We have a grouping problem. I'm going to take out a 9x, x minus 5. To match, we're going to take out a positive 1, x minus 5. So we can see that the factorization is x minus 5, 9x plus 1. So our solutions are 5 and negative 1/9. And we will find out that both of these solutions are legitimate when checking your answers. So I believe that's all the problems I had planned for this video. You'll see some challenging ones, general procedure, more basic examples. But the point is to remove the radicals from the equation, solve the resulting polynomial, and check your answers.